Top 10 Big News on Neuromorphic AI Chip Development in May 2024. May 2024 has been a groundbreaking month for neuromorphic AI chip development. With significant strides made in creating brain-inspired computing systems, these advancements are not just incremental but represent leaps toward more efficient, scalable, and intelligent AI technologies that emulate the complex workings of the human brain. This roundup highlights the top 10 developments in neuromorphic AI chips, showcasing the innovations from leading institutions and collaborations. From Intel's monumental Hala-Point system to KAIST's energy-efficient AI chip, these cutting-edge projects illustrate the future of AI computing. Here's an overview of the most exciting news in this rapidly evolving field. Intel's Hala-Point system. 1. Overview. Hala-Point is the world's largest neuromorphic system, boasting 1.15 billion neurons. Neuromorphic systems are designed to mimic the structure and functioning of the human brain. This development signifies a major step forward in creating more efficient and scalable AI systems, which could lead to advancements in various AI applications. 2. Understanding brain and neuron functions. Intel's approach to neuromorphic computing involves creating processors that mimic the architecture and functionality of the human brain. Unlike conventional processors that use binary bits, zeros and ones to process data sequentially, neuromorphic processors use spiking neural networks (SNNs). SNNs are inspired by the brain's way of processing information through electrical spikes, allowing for parallel processing and more efficient computations. 3. Evidence of brain-like functionality. Energy efficiency. Hala-Point achieves high energy efficiency, performing 15 trillion operations per watt TOPSW, which is significantly higher than most conventional AI systems. Parallel processing. The system uses a model where memory and computing power are integrated, similar to the brain's neurons. This integration allows for parallel processing, reducing data transfer bottlenecks seen in traditional systems. Real-time learning. Hala-Point can continuously learn from new data without the need for retraining from scratch, mimicking the brain's learning processes. 4. Application in AI models. The system has shown promising results in real-time AI applications such as optimizing logistics systems, smart city infrastructure management, and large language model training, demonstrating its capability to handle complex, dynamic environments similar to the human brain. 5. Current status and future potential. While Hala-Point is currently a research prototype, it serves as a significant step towards developing commercial neuromorphic systems. Intel anticipates that such systems will eventually reduce the burden of modern AI workloads and offer substantial improvements in efficiency and performance. Sandia National Laboratories collaboration with Rain AI. 1. Overview. Sandia National Laboratories, in collaboration with Intel, has deployed Hala-Point, the world's largest neuromorphic system, featuring 1.15 billion neurons. This system, based on Intel's Loihi 2 processors, aims to advance brain-inspired computing by mimicking the human brain's neural networks. Here's a detailed look at their work and the evidence supporting the brain-like capabilities of this system. 2. Understanding brain and neuron functionality. Neuromorphic computing attempts to mimic the brain's architecture by using spiking neural networks (SNNs), where neurons communicate via electrical spikes, rather than the continuous signals used in conventional computing. This design allows for parallel processing, where multiple neurons can work simultaneously, much like the human brain. Sandia's Hala-Point system employs this architecture to enhance energy efficiency and computational speed, crucial for real-time AI applications and scientific research. 3. Collaboration with Rain AI. Sandia collaborates with Rain AI to leverage these neuromorphic capabilities for solving complex problems in various domains, including scientific research, medical diagnostics, and optimization problems. This partnership aims to push the boundaries of what neuromorphic computing can achieve, potentially surpassing traditional GPUs and CPUs in specific tasks due to its efficiency and parallel processing power. 4. Evidence of brain-like functionality. Energy efficiency and performance. Hala-Point can execute up to 20 quadrillion operations per second, with an efficiency of 15 trillion operations per watt, significantly outperforming traditional AI hardware in terms of energy consumption and speed. This efficiency is comparable to the human brain's energy use, despite the brain's vastly superior space efficiency. Parallel processing. Like the brain, Hala-Point processes information through parallel circuits of neurons, reducing the need for sequential data handling and large memory transfers, which are bottlenecks in conventional computing. This parallelism enables more complex and faster computations. essential for applications like real-time AI and scientific simulations. Scientific applications. Sandia researchers have applied neuromorphic algorithms to various scientific problems, such as modeling diffusion processes in chemistry and optimizing logistics. These applications demonstrate the practical advantages of neuromorphic systems in handling complex, data-intensive tasks more efficiently than traditional methods. 5. Future potential. While Hala Point is still in the research phase, it is anticipated to lead to breakthroughs in AI. By enabling continuous learning and efficient processing of large-scale data, its potential applications range from enhancing medical diagnostics to improving AI-driven infrastructure management, showing promise for widespread impact across various fields. In conclusion, Sandia National Laboratories' work with RAIN AI and the development of Hala Point showcases significant advancements in neuromorphic computing, drawing inspiration from the brain's neural architecture to achieve unprecedented computational efficiency and speed. New instruction set architecture ISA for neuromorphic computing. 1. Overview. The Darwin 3 chip presents a novel instruction set architecture, ISA tailored for neuromorphic computing, which significantly differs from traditional ISAs used in conventional CPUs and GPUs. This new ISA includes 10 primary instructions, and several extended ones specifically designed to support flexible neuron model programming and local learning rules. It allows for on-chip learning and scalability, essential for executing spiking neural networks SNNs efficiently. The ISA is designed to match the high spatial temporal dynamics characteristic of SNNs, enabling the chip to handle the intricate computations needed for neuromorphic tasks directly in hardware. 2. Understanding how the brain and neurons work. Researchers have made significant strides in understanding the basic principles of brain function, particularly how neurons communicate via spikes. This understanding forms the foundation of neuromorphic computing. Neuromorphic systems like Darwin 3 attempt to emulate these biological processes by implementing models such as the leaky, integrate and fire-leaf neuron model and spike timing-dependent plasticity STDP for synaptic learning. These models are converted into discrete forms that can be executed using digital circuits, allowing the chips to mimic the dynamic and adaptive nature of neural processes. 3. Evidence of brain-like functionality. The Darwin 3 chip demonstrates several key brain-like functionalities. Spike-based communication similar to how neurons communicate through electrical spikes. Neuromorphic chips use spiking neural networks SNNs to process information. This method allows for highly parallel and energy-efficient processing, mimicking the brain's ability to handle complex tasks. On-chip learning. The integration of learning capabilities directly on the chip enables it to adapt and learn from inputs in real time, similar to synaptic plasticity in the brain. Energy efficiency. By employing neuron-inspired models and specialized ISAs, neuromorphic chips achieve remarkable energy efficiency, performing computations at a fraction of the power required by traditional architectures. This efficiency is critical for mimicking the brain's high performance with low energy consumption. These advancements in neuromorphic computing illustrate a growing understanding and successful implementation of brain-like processes in silicon, paving the way for more sophisticated and efficient AI systems.
KAIST's Neuromorphic AI chip. 1. Overview. KAIST Korea Advanced Institute of Science and Technology has developed a groundbreaking neuromorphic AI chip in collaboration with Samsung Electronics. This chip is designed to emulate the functioning of the human brain, using significantly less power compared to traditional AI chips. The technology aims to enhance on-device AI capabilities, providing substantial improvements in energy efficiency and performance. 2. Understanding brain and neuron function. KAIST's neuromorphic chip is built on the principles of spiking neural networks (SNNs), which are designed to mimic the way neurons in the human brain communicate through electrical impulses. Traditional neural networks use continuous signals, whereas SNNs use discrete spikes, which makes them more efficient in terms of power consumption and processing speed. This approach closely replicates the brain's method of information processing. 3. Evidence of brain-like functionality. Energy efficiency and size. The chip consumes 625 times less power than NVIDIA's A100 GPU, and is 41 times smaller in area. This remarkable energy efficiency and compact size are critical characteristics of brain-like computing systems, which operate efficiently within limited power budgets. On-device AI capabilities. The Neuromorphic chip has been successfully integrated into Samsung's Galaxy S24 smartphone, enabling advanced AI features like real-time translation during phone calls and improved camera performance. These applications demonstrate the chip's ability to perform complex tasks efficiently, akin to how the human brain handles various sensory inputs and decision-making processes. Neural network architecture. The chip utilizes a unique architecture that combines deep neural networks, DNNs, with spiking neural networks, SNNs. This fusion allows the chip to maintain the accuracy of DNN while leveraging the efficiency of SNNs. The architecture also includes techniques to compress large parameters of language models, optimizing computational energy consumption while preserving performance. Real-world demonstrations. KAIST's research team has demonstrated various language processing tasks with the chip, showcasing its practical application and effectiveness in handling real-world AI problems. This evidence supports the claim that their system can act similarly to the human brain in processing information. 4. Conclusion. KAIST's Neuromorphic AI chip represents a significant advancement in mimicking the human brain's functionality. By leveraging spiking neural networks and combining them with deep neural networks, the chip achieves impressive energy efficiency and performance. Its successful integration into consumer devices like smartphones further validates its practical applicability and potential to revolutionize AI technology. International teams. Phonon-magnon chip. 1. Overview. The international research team, including scientists from TU Dortmund University, developed a novel neuromorphic computing hardware that utilizes phonon-magnon interactions. This chip leverages acoustic phonon and magnetic magnon waves to enhance the capabilities of neuromorphic systems. The integration of these waves aims to improve the efficiency and functionality of neuromorphic computing, potentially offering a breakthrough in AI hardware. 2. Understanding brain and neuron functions. Neuromorphic computing strives to mimic the structure and functioning of the human brain. The Phonon-magnon chip's design is inspired by how neurons and synapses in the brain process and transmit information. Phonons and magnons. Phonons are quantized modes of vibrations occurring in a rigid crystal lattice, analogous to the collective oscillations of atoms. Magnons are quantized spin waves, representing collective excitations of electron spin structures in magnetic materials. The integration of these waves allows for novel interactions and processing capabilities, akin to synaptic operations in the brain. B. Acoustic frequency range. The chip operates at an acoustic frequency above 10 GHz, a range targeted by future wireless communication standards. This high frequency allows for rapid and efficient processing, drawing a parallel to the speed of neuronal spikes in the brain. 3. Evidence of brain-like functionality. The actual evidence supporting that the Phonon-magnon system acts like a brain includes several experimental validations and theoretical frameworks. Spike-based processing. Neuromorphic systems including the Phonon-magnon chip, employ spike-based processing similar to the brain's neural networks. Spiking neural networks sends in these chips mimic how neurons communicate using discrete electrical signals or spikes. Energy efficiency. The chip demonstrates significant energy efficiency, a hallmark of biological brains. The integration of phonons and magnons reduces power consumption while maintaining high computational performance. Parallel processing like the human brain, which processes information in parallel across various neurons. The Phonon-magnon chip can handle multiple processing tasks simultaneously, enhancing its computational power and speed. Hardware implementation. The physical embodiment of spiking neural networks in hardware, as opposed to software simulations, allows for real-time and efficient processing, providing a closer approximation of brain functions. 4. Future implications. The development of this Phonon-magnon chip represents a significant step towards creating more brain-like AI systems. While it does not fully replicate all aspects of brain functionality, it introduces new mechanisms that could lead to more efficient and powerful AI hardware. The ongoing research and future enhancements are expected to provide further evidence and improvements, bringing neuromorphic computing closer to emulating the human brain. BrainChip's AIKIDA processor. 1. Overview. The BrainChip AIKIDA processor is a groundbreaking neuromorphic computing chip designed to mimic the functions of the human brain. It leverages spiking neural networks (SENS) to process information in a way that is more similar to how biological neurons function. This approach contrasts with traditional deep learning models that rely on conventional neural networks. 2. Key features and capabilities. Event-based processing. The AIKIDA processor uses event-based processing, which means it only processes essential sensor inputs as they occur, rather than continuously polling for data. This method significantly reduces power consumption and latency, making it ideal for edge computing applications where efficiency is critical. Energy efficiency. One of the standout features of the AIKIDA processor is its ultra-low power consumption. This efficiency allows it to perform high-speed inference and on-chip learning with minimal energy use. This capability is particularly beneficial for devices requiring always-on functionality, such as smart sensors and art devices. On-device learning. The AIKIDA chip can perform learning locally on the device, independent of cloud resources. This feature enhances privacy and security by keeping data processing on the device, reducing the need for data transmission and storage in the cloud. 3. Brain-inspired functionality. BrainChip claims that the AIKIDA processor's design is inspired by the structure and functionality of the human brain. While traditional processors separate memory and computation, the AIKIDA chip integrates these functions, similar to how neurons in the brain operate. This integration helps in reducing data bottlenecks and improving processing efficiency. 4. Evidence of brain-like behavior. To validate its brain-like operations, BrainChip has demonstrated the AIKIDA processor's capabilities in several real-world applications. Keyword spotting and visual wake words. The processor excels in tasks such as recognizing keywords key, hey Siri, and detecting the presence of people in images, which are common in smart home and security systems. Edge AI applications. The KAIST chip's ability to perform high-speed, low-power processing has been showcased in various Edge AI applications, proving its effectiveness in practical, real-time environments. 5. Conclusion. BrainChip's KAIST processor represents a significant advancement in neuromorphic computing, bringing brain-inspired processing capabilities to Edge AI applications. Its energy efficiency, on-device learning, and event-based processing are key features that align with how biological neurons function, making it a promising technology for future AI developments. NeuromChip. 1. Overview. Engineers developed the NeuromChip, which combines our RAM and CMOS technology to achieve high energy efficiency and parallel processing capabilities, making it suitable for various AI applications including edge computing. 2. Key features. The developers of Neurom have implemented several key features that align with how neurons and synapses work in biological systems. Computing memory architecture. The NeuromChip utilizes a computing memory CIM approach, which integrates memory and processing capabilities in the same location. This design mimics the way neurons process information and store memories simultaneously, reducing data transfer bottlenecks and improving energy efficiency. Analog to digital conversion. The chip employs an innovative voltage mode sensing method for analog to digital conversion, which is crucial for mimicking the brain's efficient processing of electrical signals. This method allows for higher parallelism by activating all rows and columns of a resistive random access memory (RAM) array in a single cycle, similar to how neurons activate in parallel networks. Neuron circuit integration. Neurom integrates complementary metal oxide semiconductor (CMOS) neuron circuits with RAM weights, allowing for flexible data flow directions and neural network inference without significant power consumption or area overheads. This integration reflects the interconnected nature of neurons and synapses in the brain, supporting complex neural functions and learning processes. 3. Evidence of brain-like functionality. Several pieces of evidence support the claim that Neurom operates in a manner similar to the human brain. Parallel distributed processing. The chip's architecture supports parallel distributed processing across 48 neurosynaptic cores. This capability enables it to handle multiple tasks simultaneously, much like the brain processes various inputs in parallel. This is a fundamental characteristic of neural networks. In biological systems. 10. Energy efficiency. Neurom's energy efficiency is a critical indicator of its brain-like functionality. The chip's innovative design allows for significant reductions in power consumption, comparable to the brain's low-energy, high-efficiency operations. This efficiency is achieved through optimized neuron circuits and RAM integration, mirroring the brain's ability to perform complex tasks with minimal energy. Hardware algorithm optimization. Engineers developed hardware algorithm optimization techniques for Neurom, ensuring the chip can support various neural network architectures with high accuracy. This approach reflects the brain's adaptive learning processes when neural connections strengthen or weaken based on experience and learning. 10. 4. Summary. While Neurom demonstrates several characteristics of brain-like processing, such as parallelism, energy efficiency, and integrated memory and computation. It is important to note that these systems are inspired by, but not identical to, biological brains. Neuromorphic chips like Neuromorphic to capture the efficiency and functionality of neural processes, providing a foundation for more advanced AI systems that could one day rival the capabilities of the human brain. ABIMS North Pole Chip. 1. Overview. ABIMS North Pole Chip is a state-of-the-art neuromorphic processor designed to revolutionize AI hardware with a focus on energy efficiency and speed. Building on the principles of their earlier True North chip, North Pole integrates compute and memory in a novel way, mimicking the architecture of the human brain. It incorporates 22 billion transistors within 800 square millimeters, offering a high level of performance in tasks like image recognition and natural language processing (NLP). 2. Brain-inspired design and functionality. The architecture of North Pole draws significant inspiration from the human brain, particularly in its modular and distributed structure. It uses a combination of dense on-chip networks to interconnect its cores, similar to the brain's white matter and gray matter pathways. This design allows for highly efficient spatial computing and data locality, significantly reducing latency and power consumption. 3. Evidence of brain-like behavior. Energy efficiency and performance. North Pole is reported to be up to 25 times more energy efficient than conventional PUS. It achieves this by closely integrating memory with compute units, reducing the need for data transfer between separate memory and processing units. Neural network inference. The chip excels in neural network inference, running AI-based image recognition 22 times faster than current chips. This capability demonstrates its potential to process complex AI tasks in real time, similar to how the brain processes information. Modular and scalable design. North Pole can scale out by connecting multiple chips to handle larger neural networks, akin to how different regions of the brain work together to process information. This modular approach allows for greater flexibility and efficiency in handling various AI models. 4. Practical applications and limitations. While North Pole shows great promise in AI inferencing tasks, it is primarily designed for specific applications such as computer vision and speech recognition. It currently supports smaller models suited for enterprise needs and edge applications. However, its architecture is not yet capable of running very large models like GPT-4, which still require more traditional pure-based systems for training. Inatra's microcontroller. 1. Overview. Inatra's spiking neural processor, Tone, is an ultra-low-power neuromorphic microcontroller designed for always-on sensing applications, particularly in power-limited and latency-critical devices. This microcontroller integrates an ultra-low-power spiking neural network (SNN) engine with a RISC-V processor core, allowing it to process sensor data efficiently and quickly. 2. Brain-inspired design. The spiking neural processor Tone mimics the brain's mechanisms for processing sensory data through SENS. These networks use event-driven processing, where information is represented by precisely timed electrical spikes, similar to how neurons communicate in the brain. This allows the Tone to perform tasks like pattern recognition, and signal processing with high energy efficiency and low latency. 3. Applications and efficiency. The tone is particularly suited for applications in wearables, smart home devices, and other IoT devices that require continuous, real-time data processing. It operates at suboptimal power levels, enabling battery-powered devices to achieve unprecedented power performance gains. 4. Sense and biological neurons. Inatra's microcontroller employs sense, which closely mimic biological neurons. By processing information through discrete, time-based event spikes. This event-based processing allows the tone to handle tasks similarly to the human brain, particularly in recognizing temporal patterns and processing complex signals efficiently. 5. Evidence of brain-like functionality. Evidence of the tone's brain-like functionality is demonstrated through its ability to perform rapid pattern recognition and signal processing tasks with very low power consumption. By leveraging the inherent temporal processing capabilities of sense, the tone can handle tasks that require the identification of time-based patterns, akin to how the human brain processes sensory inputs. Intel's Loihe 2. 1. Overview. Intel's Loihe 2 is part of its Neuromorphic computing initiative, aimed at developing processors that mimic the structure and function of the human brain. Loihe 2 builds on the foundation of the first Loihe chip, enhancing its capabilities and efficiency. The chip is designed to handle complex AI tasks more efficiently by simulating neural networks at a hardware level, using spiking neural networks sense, which closely resemble the communication methods of biological neurons. 2. Brain-like operations. Loihe 2's architecture incorporates features that allow it to process information in ways similar to the human brain. It utilizes sense when neurons fire spikes, discrete electrical signals to communicate with each other, much like how neurons in the brain communicate through synaptic activity. This method allows for parallel processing and low power consumption, making it highly efficient for specific AI workloads such as pattern recognition, real-time learning, and adaptive control systems. 3. Neuromorphic features and improvements. Scalability. Loihe 2 supports a higher number of neurons and synapses compared to its predecessor, allowing for more complex and scalable neural networks. Efficiency. It achieves significant energy efficiency, performing AI, inference, and solving optimization problems, using 100 times less energy than traditional CPU and GPU architectures. Flexibility. The chip supports flexible neural network configurations and can be reprogrammed to adapt to various tasks without needing to redesign the hardware. 4. Scientific basis. Intel's neuromorphic chips are grounded in decades of neuroscience research. While they do not replicate the brain perfectly, they draw inspiration from known neural mechanisms to improve computational efficiency and capability. The spiking model used in Loihe 2 is based on well-established principles of how neurons fire and process information in the brain. 11. 5. Evidence of brain-like functionality. Neural emulation. Loihe 2 can emulate various neural dynamics and plasticity rules, allowing it to adapt and learn from new stimuli similarly to biological brains. This is demonstrated through its ability to perform tasks that require learning and adaptation, such as recognizing patterns or optimizing routes in real time. Energy efficiency, the chip's ability to perform operations with minimal energy, closely mirrors the brain's efficiency in processing information. This has been validated through benchmarks showing significant energy savings compared to conventional AI hardware. Performance metrics. Early results from Hala Point, a neuromorphic system utilizing Lohe2, show that it can achieve operational speeds and efficiency that are orders of magnitude better than traditional processors, indicating that it effectively emulates some aspects of brain processing. DeepSouth machine. 1. Overview. The DeepSouth machine is a neuromorphic computer developed by the International Center for Neuromorphic Systems, ICNS, at Western Sydney University. It aims to emulate large networks of spiking neurons at a rate of 228 trillion synaptic operations per second, which is comparable to the rate of operations in the human brain. Here's an in-depth look at the key aspects of this machine and its relation to brain function. 2. Understanding of brain and neurons. Neuromorphic computing aims to mimic the structure and function of the human brain, specifically the neural networks that process information. Traditional computing systems process data sequentially, whereas the brain processes information in parallel using vast networks of neurons and synapses. 3. Evidence of brain-like functionality. Spiking neural networks SENS. The DeepSouth machine uses SENS, which are designed to simulate the way neurons communicate in the brain. In these networks, information is processed via electrical spikes rather than binary code, allowing for more brain-like information processing. Synaptic operations. The machine performs synaptic operations at 228 trillion operations per second, which is akin to the synaptic activity in the human brain. This high rate of operations demonstrates the machine's capability to handle complex, brain-like computations. Energy efficiency. One of the significant challenges in neuromorphic computing is achieving energy efficiency, similar to the human brain. Early results from Hala Point, a similar neuromorphic system, showed high energy efficiency, achieving 15 trillion operations per watt TOPSW. This efficiency is crucial for mimicking the brain's low-power processing capabilities, parallel processing like the human brain. The DeepSouth machine can process information in parallel. This is a key feature of neuromorphic systems, enabling them to handle multiple tasks simultaneously and efficiently. 4. Applications and research. Optimization problems. Neuromorphic systems like the DeepSouth machine are well suited for solving complex optimization problems. These include tasks that require searching, planning, and following the shortest path in a map, which are computationally intensive but benefit from the parallel processing capabilities of neuromorphic systems. Scientific research. Sandia National Laboratories, in collaboration with Intel, is using similar neuromorphic systems for advanced brain-scale computing research. This research focuses on solving scientific computing problems in areas such as computer architecture, device physics, and informatics. 5. Summary. The DeepSouth machine represents a significant step forward in neuromorphic computing by closely emulating the brain's processing capabilities. Its use of SENS, high rate of synaptic operations, and energy efficiency are key factors that align it with the functionality of the human brain. While the field is still developing, these advancements provide strong evidence that neuromorphic systems can act like the brain, potentially transforming how we approach complex computing tasks. Overall summary: the advancements in neuromorphic AI chip development in May 2024 showcase significant strides in mimicking the human brain's structure and functionality to enhance AI efficiency and scalability. Key developments include Intel's Hala Point system. This system, featuring 1.15 billion neurons, leverages spiking neural networks for high energy efficiency, parallel processing, and real-time learning. It shows promise in AI applications like logistics and smart city management, although it's currently a prototype. Sandia National Laboratory's collaboration with Rain AI deploying Hala Point. This partnership aims to solve complex problems in research and medical diagnostics, showcasing superior energy efficiency and performance through parallel processing. Darwin 3 chip introducing a new instruction set architecture ISA for neuromorphic computing. The Darwin 3 chip supports real-time learning and efficient processing through neuron-inspired models. KAIST's neuromorphic AI chip developed with Samsung. This chip is highly energy efficient and compact, integrated into smartphones for advanced AI capabilities like real-time translation and improved camera performance. Phonon-magnon chip utilizing Phonon-magnon interactions. This chip enhances neuromorphic computing's efficiency and functionality, providing parallel processing and real-time capabilities similar to the brain. BrainChip's Akida processor designed for edge AI applications. The Akida processor uses event-based processing for low power consumption and integrates learning capabilities directly on the device, enhancing privacy and security. Neuron chip combining our RAM and CMOS technology. The Neuron chip supports parallel distributed processing and high energy efficiency, reflecting brain-like neural processes. IBM's North Pole chip. This processor integrates compute and memory for energy-efficient and fast AI tasks like image recognition, drawing significant inspiration from the brain's modular structure. Inatra's spiking neural processor, Tone, an ultra-low-power microcontroller, designed for always-on sensing applications, leveraging sense for efficient and rapid pattern recognition. DeepSouth Machine, a neuromorphic computer that emulates large networks of spiking neurons, demonstrating high synaptic operation rates and energy efficiency, ideal for complex optimization problems and scientific research. Overall conclusion: the neuromorphic AI chip developments in May 2024 represent groundbreaking progress in creating AI systems that closely mimic the human brain. These chips demonstrate impressive energy efficiency, real-time learning, and parallel processing capabilities, paving the way for more advanced and efficient AI applications across various fields. As research and development continue, these technologies hold the potential to transform how we approach complex computing tasks, bringing us closer to achieving AI systems with brain-like functionality.